in saturation. And so in particular, you want this voltage difference to be small, which in practice can be difficult, particularly if you go to modern technology, in which you want very small voltage variation. And so recently, an alternative solution is to realize a linear differential equation, like the one we saw last week. So first order filter, the simplest dynamical system, which is time derivative of a variable equal minus that variable plus some input. So the goal is to realize the same differential equation as last week, but in a technology, in a design that's more compatible with modern CMOS electronic implementation. And the idea is to use the translinear principle, which I won't give details, but the idea is quite simple. So the idea is that, remember that in CMOS, you basically have that currents are proportional to exponential of voltages. And by Kirchhoff law, we know that the sum over all the voltage drops in a closed loop circuit must be equal to 0. And so now if you take the exponential of this sum, what you have is that the exponential of the sum of all the exponential drop in a circuit must be equal to 1. Or in other words, if you use this relationship here, that the product, now not the sum, but the product of all the current through the same closed loop to which you're applying Kirchhoff law. So this is the basic relationship that I want to use. Let me just not make mess with this. So if you use this relation, now you have that the product, not the sum, of all the current flowing in a closed loop electrical circuit must be constant. So this simple observation, if you apply it to these circuits, what you get is this relationship between the current that flows through this transistor, the current that flows here. So this is I threshold, this is I1, just to make it, yeah, I threshold is here, I1, and so you have the product that I threshold times I1 must be equal to the product of I2 times I out. And then you can write essentially Kirchhoff's law for this system, use the exponential relationship between voltages and current, do some algebra, use some approximation for the regime in which your equation will be valid, and eventually you get to this differential equation. So this was fast. If you're interested, we can analyze this circuit in more detail. Just drop me a message and we can rediscuss it. But the idea is that with a very small number of transistors and in a way that's very compatible with modern technology, you can realize this linear first-order differential equation. And now what you need to build neuromorphic dynamics is some form of nonlinearity that you can interconnect with this linear first-order differential equation. And the design that we developed in collaboration with the University of Zurich is this one. So again, I don't want to bore you too much with a detailed analysis of this sigmoid. I just want to give you a little bit of insight of what's going on. So first of all, you see that here what you can recognize. Let me change color maybe. What you can recognize is a block that we saw last week. That is a Hurren mirror. That basically take the input current that flows here, so I in, and copy it into this branch here. So what you have here is a copy of the current that flow here. So this is the input of your system. So if we start to represent this as a block diagram, you have the current I in that enters and the current I out that comes out of it. So the current that that flows here is your output. And in between, you have this circuit which looks complicated, but actually what's going on is quite simple in the sense that, so first of all, what you have here, the pair of transistor M1, M2, is what's called a comparator. So I don't know if you saw this type of circuit in the electronic course that some of you already took, but the idea is that so you have a NMOS here, a PMOS here. So remember that a PMOS let current flows when the input is when the voltage that you apply here is low, whereas um, an NMOS let current flows when the voltage that apply here is high. So now, because you have this branch that connects the transistor, this means that if the voltage here is low enough, then basically this PMOS will be on and you will force current through this branch. Whereas if this voltage here is too high, then this PMOS will shut down and no current will be flowing here. And the threshold at which you turn the current on and off is determined by V0. So you can imagine that there will be current flowing inside here, basically when V in is smaller than V0. Imply current through through M1 to the transistor M1. So now, if there is not this branch here, then this means that this voltage will be shorted to VDD essentially, and so you will have this voltage to go out very rapidly, to go up very rapidly as soon as there is current flowing here. But this is not the case because you have this series of diode-connected transistor that we saw last week that's basically steal some of the current, and instead of let it flow down here, make it go toward this branch up there. And so it's such a way that if a standard comparator has a characteristic from V in to V out that's very steep, it's like a step. As soon as you arrive at V0, you go from very low to very high at your output. This series on transistor here makes this relationship much slower. And so basically what you have now, if you look at the relationship between V in and V out here, is basically a sigmoidal relationship like the one that I'm showing here. And then at the output, if you see, you have another voltage to current converter. So instead of reading out a voltage, what you are reading out is a current that's your output. So long story short, this circuit uses a current mirror comparator and a slowing down circuit, if you want, that creates a sigmoidal relationship between the input current here and the output current at the other side. So what we have now, that's what we use in our lab to build neuromorphic circuit, is this current mode sigmoids. That's the linear part of the system we design. And together with it, we have the DPI that we just showed. That's this filter we just saw here that maps input current to output current through this linear differential equation. So just to remember, what this guy is doing is solving, essentially providing an analog extremely low power implementation of the differential equation tau I dot equal minus I out plus again times the input current. Okay, so now we have these two blocks, and we can start interconnecting them to realize something that looks like a neuron in terms of dynamics. And this is what I'm going to start to present now. So you will see more of this. So about the neuromorphic neuron that we designed here in our lab, thanks to the presentation of Laurice. So next Monday, I won't be present in the lecture, but you will. So three of my PhD students will present their project, and in particular, Laurice will present what he has done to design our neuromorphic neuron, and then another students will talk about how to apply this neuron for controlling mechanical systems, and then a third student, Rodrigo, who's a former student of UNAM, will present more modeling ideas on how to use a similar approach, but to understand how we control walking and standing on rough terrain. And so the neuron design that Laurice will present you is based on what's called a mixed feedback design. So I don't know, did you cover mixed feedback, Omar, during your lecture?
Yes.
Okay, so you already know the notion of okay, so you have already seen the fact that you can understand a spike, and then when you go to multiple scale, a burst as the interleaving of fast positive feedback. So this will be given by sodium current mostly. And then maybe you have potassium current that implement slow negative feedback that's responsible for ending the spike. But you also have the inactivation of sodium current that are responsible for this slow negative feedback. And then if you want to generate multiple time scale spikes that here burst, then you need source of positive and negative feedback, but at slower time scale. And so burst initiation, which corresponds to a slow positive feedback phenomenon, this is implemented by calcium current mostly. And the end of a burst and the repolarization period after a burst, which is a form of ultra slow negative feedback, is mostly implemented by calcium activated potassium current. And so the approach that Laurice followed to design his neuromorphic chip is not to try to really re-implement all the kinetics, all the detailed kinetics that you find in neurons. These would be hopeless because you have too many parameters, you have too many details, you have really absolutely no hope to try to re-implement the same details into CMOS hardware because of mismatch, because of the technological problem that you have in this type of technology. But the idea is just to re-implement the feedback structure of neuron, so the coexistence of fast positive, slow negative, and on top of it, slow positive, and then ultra slow negative feedback. And entering here, you have the input current, and in neuron you have the membrane potential at the output of your circuit. Because we are working with current mode circuits, instead of having a voltage, we have a membrane current instead of a membrane potential. Everything is about current in our design. We have no voltages, essentially, or voltages are hidden, but it doesn't matter. You have an input variable, which is the applied current, and an output variable, which in neurons is a voltage, in our case is a current. What's important is to re-implement the same feedback structure to achieve the same qualitative behavior as real neuron, but on power efficient and small electronic design. And so the idea is to use the two building blocks that we have. So when you see this transfer function, this corresponds to a DPI with time scale tau f. So remember that in this neuromorphic realization of this differential equation, you have this time scale tau that fixes the time scale of integration of this first order linear differential equation. And so this is a time scale that you can fix by fixing the size of the capacitor that you use in your circuit or other parameters. The expression for tau, you can find it here if you're interested. So it depends for sure on the capacitor that you put here. It depends on the thermal voltage of the transistor. It depends on the factor, on the kappa factor of the transistor, and on a parameter that is I tau. This is the current fixed by this transistor here. So altogether, this determines the integration time constant of your first order linear differential equations. And so the first DPI is the fast DPI. So this is kind of the equivalent. The output here is the equivalent of a neuron membrane potential. And the neuron, this sort of membrane potential, this fast current, is fed back into these blocks and back into the fast DPI, exactly like it happens in a biological neuron. And so let's dissect a little bit what's going on here. So first of all, this current is fed through a nonlinearity, the sigmoid that I just described over here. And so you have this first branch that, if you see, flows here, then here, and you have a plus here, and then you have a plus here. So this first loop corresponds to the fast positive feedback loop of a neuron. Then you have a second DPI that creates, so here again, you have a DPI here and a DPI here. This time with a slow time constant, and the third one with an ultra slow time constant. And so this DPI here creates the slow dynamics that you have in neurons. And so it mimics what happens with inactivation of sodium, activation of potassium. And on the slow time scale, you have two coexisting effects. So first of all, you have a linear, so you see here you have the current that enters the DPI. The DPI is a linear differential equation. And then the output of this linear differential equation is fed directly through here, but now with a minus sign. And so this branch here corresponds to the slow negative feedback of a neuron. And together with this, you can also take the same current, and instead of using a second DPI, which would take a lot of space on chip, you plug the same current inside a sigmoid, and this time with a plus. And this provides you with the slow positive feedback of a neuron model. So you already have fast positive, slow negative, slow positive, and everything is fed back into the membrane dynamics. And eventually you want the ultra slow negative feedback to, so here as well you have a minus, and this provides the ultra slow negative that mimics calcium activated potassium current. On top of this, what Loris did was to take the output of the slow DPI and also use it to change the gain. So this is, it's not an additive input, it's a gain modulation input with a minus. And so what this does is mimicking essentially the inactivation of sodium current. So each time the slow variable goes up, it provides low positive feedback, but it also ends spike. So it tweaks down the gain of the fast positive feedback in such a way that instead of having fat spike, you have very narrow spike like in actual neurons. And if you want, you can also do the same from ultra slow to slow. So this would be like the equivalent of the inactivation of, for instance, T-type calcium current. something that acts in the same way. And this can be useful to have effects like hyperpolarization induced bursting, rebound bursting, etc. So just to give you an idea of what his... so do you have questions of this on what I've said until now? Okay, if there are no questions, I will show you a little bit what his probably I will update the presentation to put a better. But let me do it now. 1 second. We'll put a better figure where you can see more what chip design look like. So so then I will, well, I think we can leave it like this, or let me put it, well, put it in a new slide. Okay, so just to give you an idea, this is what you would do if you design chips. You will basically be drawing transistors and capacitors. So maybe you can see here these little squares. Those are capacitors. Maybe here, if you zoom more, you will see transistor. And so what really you are doing, if you go back to to last week's lecture, is really to draw where you want your gate, where you want your drain, where you want your sources. So with different color, you indicate to the foundry where you want different semiconductor pieces, different metal wires, and so on and so forth. And you do all this inside a simulation software that tells you if you made error, essentially. So to give you an idea of the sizes, what we are looking at here, well, let me change color. So this is more or less 1 millimeter. This whole site, and okay, these so we and other students lend us some space on this chip, but so this is another project. Loris neurons are here. This block that you see here are 16 neuron. You can even count them. So if we zoom inside a little bit, you can see you have 1, 2, 3, 4, and 1, 2, 3, 4. So this is a 4 by 4. So it's not a network. Neurons are not interconnected yet. These are just to test whether they do what they should do. But so in an area which is more or less, I think this is more or less 0.1 millimeter, and this is around 0.67, I think. It packed 16 neurons. And each neuron, it will tell you more about this next week, but each neuron consumes more or less 1 nanowatt to be in any of the modes it can be. And in particular, in his design, he has a single parameter that allows to change the neuron behavior between tonic sparking, tonic bursting, or even stronger tonic bursting. And if you start to play with this parameter that change the behavior, so you see here you are tonic, and here you are bursting. And on the horizontal axis, you have the applied current. So here this is I up. So you see that you can switch from a very linear encoding of the stimulus strength, like here, so where it's passed from low frequency sparking to high frequency sparking as a function of the applied current, so a very linear neuron, to a neuron that is silent, and then as applied current increases, switches on this rhythmic bursting behavior. Any question? And again, all of these was, so I think you agree that the traces are quite physiological. We didn't copy conductance-based model. We just re-implemented the mixed feedback structure, and what we get is something I think that is quite that works quite well. That looks quite a lot like an actual neuron. And what
Alessio,
you can do is also
Alessio, I missed most of the lecture, but the idea is to use the same neuron, or do you have an idea to make like different kind of neuron?
so you can do different types of neuron by putting them in different regimes. So for instance, if you imagine interneurons won't really be bursting, for instance, if you want to build network that mimics the cortex, maybe you have pyramidal neurons that can be actually modulated between these regimes. Then maybe you have interneurons will be mostly spiking at high frequency, like here. And so by setting, so let me go back to the schematics. So you see that in the sigmoid, for instance, you have various voltages like this one, like this one, and this one that are essentially parameters. So by setting this parameter to different values for different neurons, you can have networks of heterogeneous neurons, each of them with their own intrinsic sparking characteristics.
Yeah, I understand that, but I am asking if what's your plan? Do you have an idea to have heterogeneity, or do you want at the beginning to have like homogeneous
Okay, so
circuit?
let me go back.
Okay,
Let
okay.
me, I will, so um, one thing that we have to consider in this hardware is that because we are using so just to so I want to explain what mismatch is, because it's really related to neuronal variability and is essentially hardwired in the technology we use. So again, if you when you design a chip, what you're doing is literally telling I want these you're let me go back to this drawing here. um, I want this width to be, I don't know, for example, W should be 0.5 micrometer, and length and L should be, say, 1 micrometer. So you're asking the foundry to be very precise about the size of the area where they put these semiconductor pieces. And if you remember from last week, if the width and the width and the length of your transistor change, and we saw these in the Hurren mirror. Let me go back. So the input-output characteristic of the electrical property of your transistor will change as soon as the width and the length changes. And so because you are working at such small scale, there will always be, so if you take two identical, so two transistors that in your mind will be identical, then in practice, they will never be identical. So either you do it by design, like in Current Mirror, because you want some gain, or otherwise, each time you put a transistor on a chip, you will get something that's slightly different from its neighbor. And moreover, because of the technology they use, different part of the chip, different part of the wafer where your chip is put, will receive different amount of doping. So even the properties of the semiconductor will be different. So let me go back to the micrography. So say a transistor that you have here will be different from a transistor that's here, although you ask them to make them identical. Because of the sizing,
You are talking about like an intrinsic variability because of
yes,
the okay,
yes.
but how big is this variability? Do you have an idea or?
So it's very difficult to control. What I can tell you is that, and probably I will ask Loris to give you like actual experimental results next week. This is part of the paper he's writing. He's just started making the measurements because we received the chip 1.5 months ago, and is currently measuring it. But the variability is quite large. So the variability is large. comparable to the one you have in biological neural networks. And so these are simulations, and these are simulations, not Julia or Python. These are simulations made in the software that you use to design this chip. So they're quite trustful to the reality. But then when you have the actual chip, mismatch appears a lot. And so his design is robust, meaning that he has essentially almost 100% of neurons that at least in certain parameter range do what they should do. But at the same time, if you take two neurons and put the same parameter, they will be different. And how different depends on how far they are on the chip, how precise was the lithography process, and so on and so forth. And so this is what's illustrated here, that in software, in simulation, so in this type of software, you can ask the software to simulate mismatch, to implement it artificially. And so this is the base pattern, the nominal pattern that you would like to observe. And this is when I think you put 20% mismatch between these two neurons. And as you can see, the behavior changed quite a bit, but the basic rhythm is very robust. So essentially, well, the orange neuron is basically untouched. The blue neuron sometimes make a slightly faster burst, but the qualitative behavior remains. Something
And
that
Alessio, do you have an idea which is the most influential factor for this variability? The doping?
the doping and the sizing. So
The
so
doping and
the sizing happens everywhere. So even two transistors that are one beside the other will have slightly different sizing. So that is kind of the local mismatch, and then you have more global mismatch, meaning that two transistors. So once you say, okay, let's produce 50 chips because now we have something that works pretty well. We want to use it for robotics application, and so this 50 chip will be. So when you have a wafer, I think a wafer is a few centimeter, and these in this few centimeter disk, you have many chips. So many copy of the same chip that then are cut, and they become what they should become. And so a transistor here will be very different from a transistor here, because the way in which they put the product that dope this wafer diffuse in different way. It's not a perfect process. So essentially, doping here will be different from doping here, and this is what's called the systematic mismatch. So you have transistor mismatch, which is even for close by transistor, and then systematic mismatch, which is mismatch due to the fact that they're in different parts of the wafer. And this has always been seen as a problem by neuromorphic engineers. And I think thanks to what we know from our collaboration, what we know from the collaboration with Marder, we know that actually we can exploit this variability. We are not, so for the moment, people have always tried to see it as an enemy, something that must be reduced by force, by tuning, and so on and so forth. I think we know that we can probably exploit this variability once we are in an embodied context, once your network is supposed to learn something about the external world. So I think everything that has been discovered at the population level in terms of mixed selectivity and variability is super important to understand how to use mismatch in a constructive way. And for more rhythmic type of things, well, all the work from Yves Marder, I think it's really what we should base ourselves on to exploit this more than see it as a failure of this design.
Right.
Okay, so I will now move to share another window. So I think I didn't share anything last week, no, Omar? I forgot completely.
Yes.
Okay, I mean, I didn't forget. I also wanted to finish annotating these slides. So now that these slides are finished, and I will also finish to present the keynote part, and then I will move to today's lecture. So you see again keynotes, right, at the moment?
Yes.
Okay, so now I will go back to, I hope it was not too technical, for sure it was, but I wanted to give you really a little bit of taste on how we design these circuits and how we put transistors together to really do these things. So this is an actual measurement from. So this is a photo of the chip Luis is using, and this is a video of neuromodulation on chip. So as you saw, you see that you have a very nice transition from a tonic spiker to doublets and then fatter and fatter bursts. And so he's currently characterizing the effect of mismatch of various parameters on the behavior of these neurons. He has much better result at the moment that he will show next week. On the theoretical side, so I'm loving working with hardware, and I think it's super exciting to have something that works in the real world. But I'm also a theoretician, and so something that we are developing at the moment with Fernando Castaños, who's in Simve staff, and also with one of my students here, Christian, who will present next week, is trying to develop a control theory for neuromorphic control system, where essentially the idea is that instead of having either analog or digital signals that travels in the wires or in the information channels, so this can be an actual wire, it can be a Wi-Fi, it can be an Ethernet, it can be whatever you need to communicate between the plant you try to control and the controller that tries to make the plant do something. So this is the goal of control theory. This can be a robot, it can be a chemical plant, it can be a plane, it can be a drone, it can be whatever you need to control and make something you want to do. You want it to do. So the approach on neuromorphic control is that the signal that travels between what you want to control and the controller are, like in nervous systems, only spikes. So the only thing that travels in these cables are events, so the engineering equivalent of a spike. And when you do this, well, essentially you need to redevelop control theory. So control theory is a theory that exists since the 50s. Believe it or not, anything that actually works in the real world, beside asking ChatGPT how to solve your problems, I mean your exams problem. So if you take a plane or a chemical plant or a car or whatever works in the real world, uses control theory. There is no deep learning, there is no artificial intelligence in the sense of ChatGPT. Everything that really works in real life still use plain old school control theory. Why? Because with control theory you have guarantees that a plane won't crash, that a chemical plant won't explode, and so on and so forth. So you are not giving your intelligence in the hands of a machine. You're actually building the control system and designing it yourself. So what you're trying to do now is to extend.
So wait. It's, for the student, I believe that that's really important. That even if nowadays, artificial intelligence and deep learning and everything is everywhere, or we believe that are everywhere, it's really impossible to compute how stable, how steady are the processes. So because of that, if we want to be sure that something is going to fly or something is going to be stable across time or something, is made employing this control theory that was developed so many years ago, and Alessio is one of the reference across the world, probably, or at least.
No, not really. I mean, I'm not a control theorist in origin. I'm a physicist like you, but I think I got fascinated by control theory mostly to model the brain. But then I started to realize that, well, if you want to build things that work, it's the only solution. So I think like ChatGPT and deep neural network and all these kind of things all exist in the cloud, all exist to learn your tastes, to suggest grammar solution to when you write sentences, so they're useful, but only in the cloud, or maybe for some toys. So maybe you have
the problem that Alessio is talking to you is that in ChatGPT and all these in artificial intelligence, we don't know when it's going to fail.
Exactly.
So if we don't know when it's going to fail something, well, we are in a problem. Because if you are taking a plane and you don't have an idea if it's going to fail or not, well, imagine what might happen. So yeah, this
So there are
is
people in our lab, one of my colleagues in particular, that whose objective is also to make artificial intelligence more reliable by bringing neuro-inspired ideas into the picture. And actually, the end term objective is maybe to have some part of the system that uses some form of automatic learning, some form of artificial intelligence in the sense of neural networks, but maybe for adaptation, maybe for tuning some parameter. What's
okay.
important is
That's great.
that what's really make the system stable, what's really make the system work robustly, that should be something that we understand completely. That cannot be a black box. We should be able to design this, if you want, this internal loop, the one that makes a plane flight, we should hardwire it in the same way as evolution hardwired spinal cord circuits and um, um, lower part of the brain, all the evolutionary conserved part of the central nervous system are hardwired. They are not learned. They are not something that we develop. We learn. Maybe we tweak some bias while we learn how to walk, but the walking system, the walking circuit, is hardwired by millions of years of evolution. And in the same way, what we have to keep on doing if you want to build something that works is to hardwire the control loop and then maybe exploit all of these all of any database approach, maybe to make it more adaptable, to make it being able to face unforeseen solutions, unforeseen situation, and so on and so forth. But there must be something that we know exactly how it works and about which we can give guarantees that it won't fail up to a certain point at least.
And related with that, I believe that all the evidence that we have till now is that the thalamus is working like some kind of feedback signal. So the feedback signal apparently in the brain is made by the thalamus, and the thalamus, one of the something that in evolution was much before than the cortex, and is related with everything that is Alessio telling you now. So yeah.
So of course, the taking inspiration for the brain is something that, so in designing this control loop, what for sure we can do it that many few people did in a good way, because few people has the knowledge that Roman, for instance, has about how these control systems work in the head, is to use this knowledge that we are discovering about the functioning of the central nervous system for more efficient, more adaptive, more clever, more intelligent design, but more intelligent in the sense of biology, not in the sense of ChatGPT. And so now the problem is that there is a theory of control for analog signal. There is a theory of control for digital signal. There is basically no theory for spiking control systems. And this is part of the research that we are doing. And Christian will show you something about how to design. So not really, he won't really go into the details of the theory. I think he will mostly explain so the way in which he engineered this control loop to achieve a simple control objective, but that still, I think, shows all the richness of these problems. And this is, I mean, I think I will let him explain, but Christian will go through what we're showing here in more detail. So how he designed these blocks and these blocks. So how he really use these sigmoids and first order filters to realize a control system that simply by sending spike is able to achieve a control objective, and in particular to control a pendulum. And since the beginning, the pendulum has always been the prototypical object of engineers to develop theory, and then once you have a theory, you can scale it up to more complex problems. Um, uh, I think this is something that Christian can explain to you in maybe in collaboration with with Loris. So they did this work together in such a way that so Christian essentially developed the design, the computational primitive, and then together with Loris, they thought about how to traduce them into CMOS compatible components. So I think they will tell you everything about this next week. Um, Something that I'm just starting to develop, it's the application of all of this to soft robotics. So soft robotics is a big team that's starting, I mean, it's starting to be a very big team for various reasons. The first reason is that soft robots are much safer than hard robots because they're soft. So if you want them to interact with humans and you want a robot to be around you while you do your task or to help you bringing up boxes or building stuff, well, soft robots will be much safer than a robot made of steel. And secondly, soft robots can very naturally use their softness to adapt to the environment as well. So imagine you want to grasp an object with an unknown shape. If you have a soft robot, essentially the robot can rope around the object and lift it or grasp it in a much more robust way than if you have a very stiff hand. And by the way, our hands are soft. I mean, we're not made of jelly, we are not an octopus, but our soft, because based on muscles and tendons, essentially they are a mix of springs and dampers. And so essentially our hands are very, very soft. And the only thing we decide is more or less how strong to close. But then if you grasp an object, your hand wrap around the object automatically. You don't have to think about it. You don't need to ask your brain to decide how to move its joint to grasp an object. You just let your hand touch it, and then when you feel it's not sleeping anymore, maybe you stop squeezing and you just lift your mug or your pen and so on and so forth. And so talking about hands is very complicated. So exactly like the pendulum is kind of the toy problem to develop theory for control theory. We recently started to work with a colleague in Princeton. I mean, she's always been from her PhD thesis very kind of pushing what's called crawlers as a very natural equivalent of the pendulum, but for soft robotics. So essentially, a crawler is just a spring with a damper and two masses and some nonlinear friction on the two masses in such a way that when the spring expands, the head moves forward, but the tail remains still. And when the spring compress, the head remains still and the tail move forward. And so you have an object that very naturally can move around the environment simply by expanding and compressing a spring. And so what we're starting to do, both with this collaborator in Princeton and also with Fernando, is to think about spiky controllers for this object. So Shul is working on this. You met Roman at least, no Shul, I think Omar as well. Ian Shul is working on these projects, and in particular, how you can achieve steering and more intelligent behavior in this soft structure navigating the environment. And I think this is a project that we will develop quite a bit in my in this lab. Probably a postdoc we're starting working on really neuromorphic control for soft robots. And of course, there will be project to work on together. And something that not only me, but I think many people, actually mostly my colleague Guillaume and Pierre, works on is how to achieve neuromorphic touch. So having this neuronal circuit made of modulable or not neurons that are interconnected in a simple circuit and that receives analog signal from some form of touch sensor that could either be actual sensor from a person, and then you're building a brain machine interface for touch. For instance, an amputee, an amputee would be the motor part. But maybe an artificial sensor, and you want to give a sense of touch to an amputee. And so what you can put are this type of neuromorphic chip that generates at the output events that corresponds, for instance, to the orientation of an edge that's touching, recognizing the texture, detecting whether the object is leaping or not, maybe determine the shape of the object, and so in such a way that, for instance, an amputee is able to decide whether to send a descending command that will let the prosthesis squeeze more or less the object they're trying to grasp. And
Alessio, I really like a lot this picture or this yeah, because I don't know how to infer the velocity or the shape for the different combination of neurons that are yeah
I mean,
firing.
all of this is
It's
so
great.
this comes from a review paper. I mean, I don't think there is an actual chip that does this. This is from a researcher in the Italian Institute of Technology that she worked on neuromorphic touch since a lot, and we just started collaborating. And I'm sure there is not a chip that does this. So this is
Okay.
something that she's proposing. And of course, I think there is not because probably there is still lack of taking, like, for instance, what you have discovered about frequency encoding, or you told me there was also this old work from Roma where they was sliding the pen, the tip uh, of the rubber tip on the finger in one direction or the other. So I think there is still a lot to take inspiration from to really have something that does this efficiently, meaning that there is a lot of project to be done here.
Yeah, in some moment I really wanted, probably in the future, I want to do this experiment again. I believe that nowadays we have a lot of understand from that experiment, but I don't know why the people stop uh, using this kind of stimulus. Probably because it's hard to analyze, or yeah, several years ago it was really difficult to understand how different neurons combine together to estimate the velocity or something like that. Imagine that in the 90s, the people believed that one neuron can explain the brain or something like that. So now that we have moved to population code or these ideas, yeah, I believe that this experiment need to be done again. Really few people are working on that. Yeah,
There
Besmaya
would
was.
be something is occurring, but so would be would would be also nice to have like a sleep. So it's a sleep detection. So imagine, so you maybe you
Yeah.
press something on the finger and then you start to pull at a certain moment that the object will sleep.
Mhm.
I don't think this
I
ever.
would I would start with a velocity categorization or
Yeah, yeah.
direction categorization, probably both at the same at the same time. Well, one condition and the other one. So yeah, and then yeah, sleep detection is a good idea, I think. Yeah, yeah.
Okay. So this is I will show you a video about something that. So what you will see. Okay. What you will see is a robot. So which will just be, I think. Let me check. Uh, so in the video, where is it? So the square is a robot, and the arrow is a human. Of course, everything is simulated. And what you're showing, what Charlotte is showing here is, in the first case, so the robot has to avoid the human. So imagine this is a robot that helps in a commercial center and has to avoid human coming toward it. And here you have a human that maybe is walking toward a shop, but then saw another shop and changes the direction in which it's walking. And so this is the blue is the behavior of the robot with a let's say standard controller, whereas the red is the behavior of the robot with a spiky controller. And so the idea of this project is that by using spiky controller, essentially you have robot that can dribble, that can rapidly adjust their motor behavior to what, for instance, humans are doing around them. And so let me show you the simulation. So you see this the robot thing, it's going left, and so the robot with the standard behavior, it's slow in changing its behavior. With the standard controller, it's slow in changing its behavior. And so because he already decided to avoid on the right, it crashes with the human, whereas the red one really does like a football player when it dribble around one of the opponents. And so this idea of agile control, I think the rest, well, this is some faceplate analysis. You will have these in the slides if you want to see it. And this is the same idea when you have three robots that have to coordinate themselves to avoid to humans, and you have robots that decides where to go, and other robots that decides who's to follow, essentially. So the first simulation was robots follows the leader, and now you would see what happens when robots, the blue and green, do not follow the next robot. And as you can see, you have, well, something that very nicely can dribble around humans and so on and so forth. And so now this idea of agile control is something that Shul will probably be developing in his PhD thesis, and that again, brain-inspired principle would be great to implement and to port. Okay, so this was to give you. So I know that the technical part was probably a little boring, but I hope with these last slides to give you an idea of why we are making these
So,
efforts.
Alessio, where are you going to put the slides? I would like to.
I would send them to in a Google folder, Google Drive folder, and I will share them.
Great. Bye.
Okay, so if there are no questions, maybe I will move forward to today's lecture, which will still be quite high level. So I'm happy to hear that you already saw the. I think I have to, yeah, I have to export them to PDF. Yeah, because I want to write. So let me just rapidly export them to PDF and yes. So you already know about the mixed feedback principle, so I don't have to recover it now. And let me open it with GoodNotes. But I want to give you a little bit of simple theoretical insight of why mixed feedback systems are probably so widespread in nature, and then connect it to some of the research we are currently doing with Roman. So I can the mixed feedback part. I think I can be very fast. Where is it? Not GoodNotes here. Okay, so again, this is something that we already mentioned. The idea of mixed feedback really came for us when we're looking at the neuronal membrane. And so the role of sodium, the role of potassium, the fact that positive feedback is really underlying the regenerative aspect of action potentials. The negative feedback is underlying the restorative aspect of the action potential. And neural activity is all about balancing these two types of feedback all over the place. So something that, okay, if you look at all the ionic current that you find in neuron, you can always classify them in terms of, so you can essentially do a remapping of all known ionic channels that you know in terms of whether they're fast positive, slow positive, slow positive, and so on and so forth, or the same thing for negative, so this will be slow negative, and so on and so forth. So you can really do a mapping of electrophysiological elements into feedback, which I think can be very useful to understand mechanisms of the brain. The nice thing is that so there are evidences. Then of course this type of work that I will talk about now has been kind of abandoned because it's a lot of work. Probably it has become kind of old-fashioned to do this type of electrophysiology at a certain point. But at least in 1991, people were still doing um, in vivo intracellular electrophysiology. And this is the work that I'm talking about is the work of Rodney Douglas, who eventually turned out to be one of the most important, the most influential people in neuromorphic engineering. And so what they did in this, I think he did this still as a student. I'm not sure, but might be. So, no, probably not. I don't know. 91, I don't know. It doesn't matter. Probably postdoc. So what they do here is that they record it intracellularly from neurons in V1 while stimulating the afferent from the visual thalamus. And the stimulation they were giving were sufficiently small not to induce action potential generation, but I'm saying something wrong. Yeah, there is no action potential here, but still sufficiently for engaging a response from the whole circuit. And so what they show here is basically what they recorded. So you see it's the response here is 20 millivolts, so everything is at threshold. And what you can see is that on a time scale of 100 milliseconds, you have, so you give an electrical pulse to this afferent pathway, and what you have is a fast excitative response followed by a slow, a kind of relatively fast inhibitory response, and ended by a much longer inhibitory response in these neurons. And so the way in which this work, I think, is really, it's like a Hodgkin-Huxley, I would say, type of paper. So really fundamental one, but for cortical circuits, because they do not only do this type of experiment, they also try to model them. And the point they make is that, okay, if you want to, so if you have just a feed-forward circuits, then essentially you cannot explain anything of what you're observing in your recording. So first of all, to have a sufficiently fast and you see you kind of have an amplification of the signal. So you have the signal arrives, and then you have this kind of regenerative part of the response that's also seen here. You need some form of recurrent excitatory interconnection between these neurons that creates fast positive feedback, exactly like a single neuron level, but now in circuits. And then if you only have this excitatory recurrent connection, then probably what would happen is that, well, your circuit will just depolarize and remain at a depolarized, still at threshold, but depolarized state. And which means that, I thought I put all the other, but yeah, okay. So in order to explain why you don't remain up, but at a certain point you go down and then go down much further, well, you need this mixed feedback circuit now at the neural population level. And so you have excitatory cells that excites inhibitory cells that are also driven by the input. And moreover, you need recurrent inhibitory interconnection between these cells in order to generate a sufficiently reverberating response in inhibitory cells that can explain this form of sustained inhibition that you see here that goes beyond the time scale of GABA kinetics, essentially. So this is just to say that mixed feedback is not something that exists only at the single neuron level. There are not many more evidences of this because, I mean, direct evidences. I think that what Roman is doing is providing indirect evidences of mixed feedback, and I will get to this in a moment. But at least direct electrophysiological evidences of spatial, so population level or circuit level mixed feedback in the cortex. There are probably not too many evidences. Probably this is one of the best one, although very old. Um, I would like now to give you a little bit of insight on, I would say that the philosophy of mixed feedback systems, or why probably evolutionary or functionally they are so widespread in the brain and beyond. So I didn't want to put reference here, but if you're interested, I can give you. I can maybe put in the folder, or if someone asks, evidences for mixed feedback structure, essentially from anything from starting from molecular regulatory networks at the subcellular level to essentially society of bees, society of humans, and all scales in between. So the more you look at systems that behave intelligently, either as single agents like single cells, or as society, including or as network like brain or societies, the more you can spot mixed feedback structure all over the places. And I would like to try to give sort of justification from an engineering perspective of why this might be the case. And the way in which I would like to give.
Alessio, one historical doubt. This mixed feedback engineering was mostly developed by Rodolphe.
Us.
By
Rodolphe, me, and Guillaume, yes. So
yeah.
this point of view is really Rodolphe, me, and Rodolphe, Guillaume, and me, yeah. So
Okay.
it started with um, well, Guillaume was already studying the dopaminergic neuron in his PhD and arrived here as a postdoc. And somehow we stumbled on this, trying to understand the dopaminergic neuron first. So really understanding the pacemaking, the very robust pacemaking of the dopaminergic neurons was what brought us to kind of discover or inventing, if you want, I don't know if, I mean, or this way of looking at intelligence through this mixed feedback lens.
So
And so what I would like to,
when was that? When was that? Like 20 years ago?
no, when I was a postdoc, so
In
2000,
Cambridge? Were you in Cambridge or
Liège,
yeah?
Liège and Cambridge. So
Okay.
2013, between 2013 and
Ah,
2015, I think I would say it's where everything mostly related to conductance-based models and electrophysiology, I think was mostly developed between 2000 before I came to UNAM essentially. And then after I came to UNAM, I I mostly started to apply the similar ideas to decision making with Naomi in Princeton. And what I will tell you is kind of a mix of the two. So I think it's mostly the neuronal part, but now also with this decision making or categorization perspective, that I think it's something that um, I think we kept on developing in our head through various projects essentially until now. I think.
could you
Uh,
make Naomi to collaborate with Rodolphe, or do you believe that is quite
no, I think
complicated?
so. I mean, the two already had their own projects. So I think, in a sense, the collaboration with Rodolphe stopped. I mean, stopped. It get to to a mature phase, and then the one with Naomi was starting, and so like all the decision making aspect, I think, came later. But I think the two are very tightly linked. So I think that what I would like to to um, to explain now is that, like in the simplest system, how this notion of mixed feedback essentially is a way of implementing, um, well, essentially intelligent decisions at any scale, in a sense, and also provide a reason for why action potential exists in the first place, for intelligence. But I think, yeah.
Something that is important from the neuroscience point of view is that some years ago, not many, 3, 4, 5, I was asking myself why the brain needs several feedback inputs. And
Several what? Sorry.
feedback, because in the brain you see feedback from different areas. Probably most of them through thalamus, or I don't know, or with different mechanisms. And there are people that are fighting what is the feedback mechanisms. And now, after talking with you, after reading a little of your work about mixed feedback, I realized that probably is something useful for the brain to have like mixed different kind of feedback. Thalamus is for sure one of them, but then there are probably several more through oscillations, through coupling between phase and amplitude in the oscillation. So yeah, I don't know exactly which is the reason why the brain is using this mechanism, but probably the idea or the evolution idea is something related what with Alessio is going to talk now. So yeah.
Yeah, then I will try to be kind of like the more theoretical part. I don't want to be super long, but and indeed I want to arrive to the two results we have together that I think show exactly what you're suggesting. That yeah, that if you start to look at your data from the point of view of mixed feedback, I think there is a lot more to be discovered in terms of this type of principles.
We need to write a perspective about that. Why it's important the mixed feedback and we
Would
don't
be
have time,
fantastic.
Alessio. Yeah, we don't have time.
Yeah. So again, as you saw, I'm in love with this system. Tau x dot equal minus x plus u. This is, I think you can you can build a saturation of linearity. So again, exactly like with what Larissa has been doing, these again would be our building blocks. Just because they're everywhere in biology. You have degradation all over the place. Of course, you have dynamics, and you have sigmoidal nonlinearity everywhere, from neurons to molecular regulatory network to sensory responsive to psychophysics to how our tastes evolves. So these are really two universal building blocks in PyTorch, in TensorFlow. So these two building blocks are all are everywhere from biology to technology, and I think it's really important to start from them to understand something general. If this was not clear, you can always, I mean, already uh, stress this in the transistor part, but you can always represent this differential equation as um, as a block that takes input u and has output x in this case. And if you write this equation in Laplace transform, I don't know if you saw Laplace transform, but derivative becomes multiplication by s, and so in Laplace transform, this equation becomes this, which means that the transfer function of the system is 1 over tau s plus 1. That is, this is a low pass filter with cutoff frequency 1 over tau. And something that I would like to stress is that this low pass filter is already a negative feedback system, because another way of representing this equation, so another block diagram representation, is to have a perfect integrator, so a block that just integrates your system, that receives input u, returns x, but now x is fed back with a minus sign in such a way that now what enters the system, you see, this is the integrator, and what enters the integrator is the input minus x. So each time you have a low pass filter, you already have a negative feedback system. And okay, each time you have a sigmoid, this is fairly standard. You can represent it as a system that takes input u and returns output j. Okay, so I think that the simplest mixed feedback systems that you can think of is a scalar differential equation that's given by this. Why is this a mixed feedback? Well, because if you use this, and this is a sigmoid, So if you use this representation for the low-pass filter, what you have is an integrator. By the way, this is essentially a model for the neural membrane, as you know. So the neural membrane is just 1 over, if instead of tau you put a capacitor, this is basically the neural membrane. If you want to if you want to map everything I'm saying to neurons, and so this is the input of the membrane, so the current flowing through it. And okay, first of all, you have the negative feedback loop. That's this one here. Maybe let me use colors. This is the negative feedback that corresponds to this term here. And on top of it, you have this new term that, what I'm doing here is that in the sigmoid, I'm not only putting inputs, but I'm also putting a function of the state. So if you put your sigmoid here, you have the inputs that enters this nonlinearity, but you also have the state that's taken from the output of the integrator and fed back here with a plus. And so you see that this differential equation is already a mixed feedback systems. It's a one-scale mixed feedback system. Usually, in Spike, we think of positive feedback as fast, negative feedback as low. Here we have positive and negative feedback that coexist on the same time scale. And why is this system useful to understand the possible conserved function of mixed feedback? Because essentially it's probably the simplest model of a transition from analog faithful to digital categorical representation. And if you know Roman's work a little bit, well, you know that understanding how this happens from sensory input to ideas essentially in the brain is probably one of the most important questions in his work. And I think this model is basically the simplest model in which we can understand this transition from an engineering perspective. So what I'm showing here is, and then I will also share with you a Julia notebook. I know you don't like Julia, but I work in Julia, so we share a Julia notebook, and I will guide you through it to show you how to use it. But this is just the results of the simulation. So what I'm showing here is the results for kappa equals 0. So no positive feedback, purely negative feedback. And what I'm doing is decreasing tau. And so what you can see here is that because you have 1 over tau, if you compute the gain of this negative feedback loop, the gain here is exactly 1 over tau. So the smaller the tau, the stronger is the negative feedback of this loop. And as you can see, is that as you decrease tau, so sorry, in dashed blue you have the input to the sigmoid. This should be, it's an old figure. This should be well, actually I forgot to update the notebook, which I will do. This should be a new. So in blue, you have the input to the sigmoid. It's your sensory input, if you want. And in different shade of grays, you have the output of the mixed feedback system for kappa equals 0, so purely negative feedback. And you see tau 0.5 means not so strong negative feedback, and tau 0.02 means very strong negative feedback. And as you can see is that as you increase the strength of the negative feedback, as this feedback becomes stronger and stronger, the output of the system tracks the input more and more faithfully. So when the negative feedback is not too strong, well, the input is oscillating, the output is also oscillating, but there is a delay, the amplitude is not really matching. Whereas if you take a very strong negative feedback, then you have the output that really tries to follow the sensory stimulus as faithfully as possible. Let's see what happens when we start to increase the positive feedback gain. So here I'm taking the strongest negative feedback, and sorry, this is the negative feedback. So fixing the tau that fixes the strength of negative feedback to the strongest one of the previous slide, and increasing the strength of the positive feedback. And again, the dashed blue curve is the stimulus, the sensory stimulus, the input. And in the different shades of gray, you have different strength of positive feedback. And in particular, dark gray corresponds to small positive feedback. Middle gray corresponds to intermediate positive feedback, and light gray corresponds to strong positive feedback. And as you can see, there is a smooth transition from a faithful representation, because you have a little positive feedback. So you see that the representation for kappa equals 0.5. For k equals 0.5 is faithful but amplified. So it is in phase with the stimulus with the sensory stimulus, but there is a little bit of nonlinear amplification of the sensory stimulus given by the positive feedback. Then if you increase it further, you already start to have kind of a not fully categorical, not fully decision-wise representation, but for sure you start to have a little bit of memory. So for instance, here the input increases, and now you have a huge nonlinear amplification of the input in the mid-gray response. And as you can see, when the stimulus changes sign, well, it takes a while for the system to switch to the other response. Why? Because the system starts to have a little bit of memory, and you can see this memory also here. So the stimulus ends here. But for k equals 0.95, it takes quite a bit after the stimulus ends to return to the basal response, meaning that now the system has a sustained but still vanishing memory. And then when k is large enough, well, essentially your system become like a digital bit, like a memory in a digital computer, meaning that if the last presentation of the input it was positive, then it will retain these observation, this category that I'm calling decision A. Maybe I should change it to category, not decision, but I think the two are kind of the same. And the last value, the last category of the stimulus is maintained in memory indefinitely, essentially, when kappa is large enough. And I think if I don't know if you already did it, Omar, to study the bifurcation of this system. Probably yes. Otherwise, with the bifurcation theory that you saw with Omar, it should be pretty easy to understand why, as you increase k, there is this transition from this type of response to this type of response. Did you see this model already, Omar, in your course?
We briefly mentioned it last semester, and it is only until next week or so that we will see it once again.
Okay, great. So you will dissect what's going on here from a bifurcation theory perspective, and I think you will find something pretty neat that explains this transition. Okay, so before going to mixed feedback in Raman's data, which is the next topic, I would like to.
I didn't know that I was going to be here, but yeah, great.
There was a surprise. I would like to know if there are questions. Otherwise, I'm going to the notebook. So let me stop sharing this and start sharing. This one. Okay, yeah. You see VS Code? Yes. So basically, what you have here, I will give you these GL files. Did you ever use Julia during during your courses until now? No. Since I'm gone, nobody's using Julia anymore.
Yeah, not recently, no.
Okay, then either you translate. I mean, you can very easily translate it to Python. But what you have here is basically the code to generate this figure. Actually, let me open another file, which just to show you something more. I didn't want to put in this lecture because I thought it would have been too much material, but I think it's nice to see it. So that's basically going multi-scale. So I wanted to give the mathematics of mixed feedback for a single scale, like in the model that we just showed. But what happens to this model if you include slow negative feedback? Well, what happens, and I think this is something that you can understand with faceplate analysis very easily. So the model I'm simulating here is, well, I will go back to the slide to write down what are the equations. But first, let me show what happens if you take this model and include slow negative feedback. Well, what happens is that, okay, you have your positive feedback system that maintains the memory of the stimulus, but eventually you would also like to forget what you saw, because maybe you have to go to do another task. And so without slow negative feedback, this memory would be maintained indefinitely. Slow negative feedback, what it does is to reset the state and brings it back to a nominal state. But there is kind of something I'm hiding here, because Roman mentioned oscillation. So what happens is that if you have, so let me simulate for maybe 100. Let me run the whole book. I don't remember if the kernel is still on. And so what I was going to show in this section here that's called fast positive feedback as negative feedback creates sustained oscillation. So is that as soon as you have fast positive as negative feedback, if you don't have a mechanism that inhibits your system, and probably this is also one of the role for inhibitor interneurons that fires all the time at super high frequency to keep the system at rest, is that if you have fast positive as negative feedback, your system, okay, will retain the memory, but as negative feedback will reset it, but to the other category, and then you will start to have essentially oscillation between the two possible category of your system, that your system can encode. And so maybe this is something that you can do as an exercise in class to basically show that if you take this system and now keep waiting, what happened? That if you want to stop this oscillation while maintaining the same gain for fast positive and slow negative feedback, then what you have to do is to know what happened to VS Code. It's responding. I don't know why it bothers me. I think there are too many points. This figure is too big. But anyway, I think I should change the time resolution. Well, it doesn't matter. If you add the constant inhibitor recurrent to the system, then you can stabilize this oscillation, and basically the system, instead of being oscillating, it will become an excitable system. So that is to say that fast positive feedback creates the emergence of categories and of categorical representation out of analog and faithful representation. And then if you want to robustly forget the decision you make in terms of category, then you also need global inhibition, which essentially putting all together creates an excitable system. And so if you believe that there are some functional mechanisms that's preserved across intelligence and evolution, that basically, and that if to be intelligent, you must integrate sensory information faithfully, but you also need to represent this information faithfully. And you also need to forget, well, essentially, you end up discovering that a spike is not an artifact of neurons, but that you must use excitability to process information in a flexible fashion. Let me turn down this because otherwise it keeps bothering me. So this is something that I didn't want to put here, but again, we can rediscuss, and I think this is more or less what we are starting to discover also in Romance data. So let me close this, and also this, and let me stop share this window and go back to the slides. Because there is no better way of seeing this principle in action in cortical dynamics. And I think the two papers we worked on, I mean, there are more, but one is published, one it's almost done. So Roman, can I talk about the Bernie's VPC paper?
Yeah, for sure. Yeah.
Okay, so the two one is the one that's already out, where we're trying to understand what's going on in the representation of sensory information in the second somatosensory cortex, and a key observation of this paper that you can find. So the biology of this, it's in all the recording that are in the paper. But let me summarize this from a modeling perspective to relate it to what we are discussing now. Is that a key observation of this paper is that attention modulates the response of a neuron in the second somatosensory cortex. And in particular, a key observation is that when the animal is given the response, so it doesn't have to pay attention to the sensory stimulus, basically all form of categorical response disappear from the second somatosensory cortex. And the way in which this can be modeled is by using exactly the principles that I just described. And in particular, so if in the model that we developed in this paper, there is a faithful neurite population, which, I mean, there is a faithful.
Alessio, 1 minute. Last semester, I talked about 1 minute about this figure, but I talk about all the other results. I don't know if the guys remember my last semester class about population dynamic, but yeah, for sure that now to explain the model is great. Okay.
So you see that in this model, the eigenmodes. So when I say an eigenmode, it's so the population has mixed selectivity. And so an eigenmode is a linear combination of neurons in this population. And so each neuron contributes more or less to faithful eigenmodes of the population, temporal or categorical. And as you can see, faithful eigenmode in this model correspond to small positive feedback gain. Temporal eigenmodes correspond to feedback gains that are in between faithful and categorical eigenmodes corresponds to large feedback gain. And a simple way of understanding what attention is doing in the somatosensory cortex is literally by reducing the positive feedback gain for categorical eigenmode in S2 recurrent dynamics. And when you do this in this model, you see that simply by reducing this gain, you have that when the positive feedback gain of these eigenmodes is large, you have these beautiful and robust categorical responses. When you turn down this positive feedback gain, all type of categorical response disappear, and everything become very faithful or at most temporal in S2 dynamics. And again, if you want to understand this, I think the figure I showed here is really what's going on. So small feedback gain, small positive feedback gain, you are very faithful. Large feedback gain, you start to have memory, and if you play with a notebook that I will send, you also have the emergence of slow negative feedback to end this categorical response and be ready to make new decisions. The other paper in which this appeared is in the context of the bimodal detection task and from data in the ventral premotor cortex. And something that emerged from dimensionality reduction analysis of the neural population of the ventral premotor cortex is that when you project the dynamics onto one of the two main principal component, what you see is kind of this rotational dynamics in which the stimulus arrive, pushed the trajectory out of the equilibrium, and then there is this kind of arch or this rotation that the neural trajectory do in the neuronal manifold, in this low-dimensional manifold that organize the population response. And so the idea was try to understand why this, if there are some simple mechanisms, some simple dynamical system that can explain this, and the answer is yes. So what you're looking at here is a sketch of the phase plane of the model that I will show in a second. And no, I don't think I put the equation, but I will write them down. Why didn't I put the equations? Well, let me copy paste rapidly the equations from the supplementary material. No, this is supplementary material. Oh, yeah, I have them on Overleaf. 1 second. No, not in Overleaf. I have them. Rotating memories. Okay, so the question are here, and probably this is also nice dynamical system that you can analyze in class. It's a two-dimensional system, but actually it's the interconnection of two one-dimensional systems. So it's the analysis is definitely doable. So these are the equations. And let me draw the block diagram representation of this system. So basically you have, so I are the sensory inputs, and the sensory input enter a first order linear filter, which gives the sensory response. And so as we saw now, this is equivalent to a purely negative feedback block. By the way, it's not explained like this in the paper, but maybe we should before submitting. Purely negative feedback. And the sensory response is fed back into, is not fed back, is fed into a dynamics that has the following form. So it has a low pass filter, so another negative feedback block. And it also has a strange nonlinearity that I don't want to enter the details here, but basically this nonlinearity has a shape like this, as a double kink instead of a single kink. And the output of this double kink nonlinearity is fed back into the low-pass filter. So this is the positive feedback branch of the system. And thanks to this structure, what you have is, so you see here, you have this double S. So this double S that you see in the faceplate that creates these 5 stable equilibria is given by this double kink nonlinearity in this model. And maybe this is something you can understand through faceplane analysis and dissecting this a little bit more in class. But basically, what you have is a purely negative feedback response for S, followed by a slightly more complicated purely positive feedback, mixed feedback structure for the mnemonic response. And so when you have these all together and you look at the response in the sensory and the memory variable, well, essentially you have a very faithful response at the sensory level. And this is normal because sensory variable is driven by purely negative feedback dynamics, so purely faithful. And then this response is mapped into a positive feedback or a mixed feedback dynamics with a strong negative feedback, strong positive feedback that transform this faithful response into a very categorical response that is category A, category null, and category B. So in this case would be tactile, nothing, acoustic. And eventually we understood that this kind of seemingly strange or unnatural circular or rotating response probably is just the effect of cascading a purely negative feedback encoder for the sensory part and a mixed feedback encoder for the mnemonic part. So I think if we start to look at electrophysiological data with this mixed feedback perspective, then probably we can understand a little more the mechanism, the dynamical mechanisms underlying neuronal population encoding. And once we have this structure, essentially we can design them into artificial machine.
Alessio, something related to what we were asking before is in the data and the artificial network, we have seen that the attractors are not symmetric, are not really symmetric as we are seeing at the dynamical system. What do you believe that is the main reason that even in the artificial networks appear this not symmetrical?
I think the main reason is that here I'm using variable that can be positive or negative, whereas neurons encodes everything in spiking rate, which are positive variables. And so once you have positive variables, necessarily your system will be asymmetric.
But this is in the biological one, but in the artificial one, I don't see
in the artificial one
quite clear
the artificial one can also be because the artificial one is using an asymmetric nonlinearity. Is using the soft plus.
Soft plus. Okay.
I think it's so. I've had the impression. So something that what one could test, for instance, and this, I mean, this could be a project per se, is to study. Let me open another. So to answer this your question and to test whether what I'm saying is correct, is to do what's called log domain analysis. And I think nobody ever did it in rate models. So essentially, is instead of working with the rate of neurons, even before doing z-score normalization, before doing anything, work with the logarithm of the rates of the neurons. And these will be the new variables. So if you have the rate of neuron I, now you define a new variable, which is the logarithm of the rates of neuron I. And if you do so, then essentially you are mapping. So these guys lives in the positive space, whereas the logarithm lives from minus infinity to infinity. And the nice thing is that this is a nonlinear space. So the positive real line is a not a linear vector space, because you cannot subtract positive number, otherwise you can go negative. Whereas here you're really in a vector subspace. So I think it would really be interesting to understand what well, population level analysis looks like, what neural network implementation of this looks like if we stop working with positive variables. And that said, this is my there is this. Let me just give an hint of something that I think could be related, which is a paper I'm giving a lecture on Wednesday, which is this paper here, which is a connection between everything we are saying and Bayesian inference. And so in Bayesian inference, taking the logarithm is very natural because Bayes rules work with multiplication and division, and so if you take the log of multiplication and division, you get sums and rests, sums and subtractions, and so taking the log is very related to. I mean, it's something that appears very natural when you try to understand what the brain is doing from a probabilistic Bayesian inference perspective. That is to say, there might be really something to do on this topic. But okay, I need to finish the lecture, and then I'm open to remain a few more minutes. But I don't know if the students want to go. Okay, something that I just briefly mentioned is the fact that once you have mixed feedback, so this transition from faithful to categorical, and you introduce multiple time scale, you immediately get spikes. So again, this is to say that spikes not at the neuron level, but at any level, are probably something much more universal that we imagine if we think in a two linear fashion. And I think what we are discovering in Roman's data points to the fact that this might be the case. And you can extend mixed feedback to network, and this is exactly what we did in the S2 paper in PNAS. And once you do this, well, essentially you immediately have a theory that explains why you have mixed selectivity, how neuromodulation can act to change the encoding of the network. You have a theory to understand network receptive fields. You have a theory to understand network spikes, and all of these are basically open field of research. That said, I think Omar already sent you the instruction for next week. So next week will be a very hand-on lecture on a full-blown neuromorphic chip that's been developed probably across 20 years by people in Germany, in Heidelberg. And
sorry. Just a
yeah.
question. Was it next Wednesdays or next week?
No, sorry, next Wednesday. So in 2 days.
Yes, thank you.
Yeah, sorry. So in Wednesday, in 2 days, we will see how to use a neuromorphic chip, how to implement bursting, how to implement neuromodulation in this chip. I won't touch how to build networks because I don't know how to use PyTorch. I don't want to learn it. But we have beautiful tutorials to build network and to do machine learning or to even model Roman's data on this chip. So I really suggest you to follow this lecture with attention because there are many projects, not theoretical as the one that I just present today, but if you are more keen onto more practical problem, I think this lecture will really interest you. And the way in which this chip was built was using transistors and capacitor exactly in the way that I explained last week and a little bit of today. So basically, of course, we want open the details of this chip, but you have everything to understand how this chip is working. I will give a very high-level description, and I think with the theory I just give you, we can really build nice project on how to use this chip for research. Okay, are there questions?
Sebastian, Fernando, I believe that you need to be in special attention for next Wednesday. Yeah, this kind of project that Alessio is talking about is, I believe that may be great to apply for us. Yeah.
Okay, so maybe next week, I mean, then after next week, if someone like Fernando, Sebastian, nice to meet you, by the way, then you want to keep on discussing, that would be great. I think the people in Heidelberg, so I need to discuss with them, but for sure they're also interested in collaborating and see applications of this chip to more neuroscience type of questions. I think that that's never really been done. So I think there is very fertile ground to do cool stuff. Okay, guys, if there are no more questions, I think I will stop and see you on Wednesday. And now I won't forget. I mean, I won't do it now, but I promise at a certain point soon, between today or maybe after Wednesday, because I'm overflow with lectures until Wednesday. But then I will put all of this material in a share file.
Alessio, let me share something that I want to discuss. Can I share?
Yes, sorry.
Yeah, something that you were talking now, and we forget to cite this paper in our last. But yeah, this one. Yeah, look, this is employing a spiking neuron, and this is made by Nestor and his college. But yeah, they show that it's a Bayesian estimator at the neural recurrent network.
Okay.
And they publish a cell report only, and they show that only using that the contraction bias it appears without asking anything, and it's all because the network makes some kind of Bayesian estimator. I was talking with Bernie that I believe that this is like the direction that we should follow in the next, yeah, for modeling spiking networks. And
so with the lecture I will give on Wednesday, maybe I will tell Bernie to come to my lecture. I will give not the spiking version of this, but the spiking version is very natural because of the rate approach, which gives this log domain encoding. But so going from non-spiky to spiky theoretically doesn't change much. Then in implementation it changed. It's really important. So the theory Wednesday week, but yeah.
Yeah, that's great. And I was really shocked because I didn't read this manuscript after we have sent the manuscript from Hector, the time. This is exactly the same task. And the same attractor, linear attractors appear with the same curve. And they argue that the curve that appear at the geometry is because the Bayesian network. It's like they are pushing to the bias. The network is pushing to the center of the network. And because of that, the network and the brain is making this contraction bias. It's really great idea. And well, it's something that
how's the paper called? Let me
yeah. This is the model.
Yeah, okay. That's exactly the model we present. So it's not a SPI. I mean, they interpreted. Oh no, it's a leak integrating file.
Yeah,
okay.
it's a leak integrating file. Yeah.
Okay. Yeah.
And they don't have so much heterogeneity, I believe. I need to check it a little more, but probably we can. Okay. Yeah, the paper is called. Yeah.
Okay. So maybe I think I will record the lecture because there are other pairs of collaborators who are interested in in that. Do they cite Rao? Can you check in the reference if they cite this paper that I mentioned? If you look for RAO Rao.
Yeah, Rao. Yeah. I know these guys, but I don't know Rao.
He also has a paper with Shenoy about using.
Yeah, Rao is famous.
Yeah, so
Uh,
Rao
we-
is the paper I will present. You saw that the reference is, I think, is
yeah.
the original paper in which introduced this idea for the first time.
Mm, Yeah. I have read the following up papers, the ones that appear after that, but after the one that you are going to talk. But
No, that's one. Yeah.
yeah, they cite all the time this work, but so it could be nice to read and to listen about that. Yeah.
I'm interested in the non-spiky version because I also want to connect it with the nonlinear opinion dynamics model, so the one with Naomi. So I think then, I mean, you can always make it excitable by adding slow negative feedback.
Yeah.
But
Now
yeah.
we can talk with Nestor. Nestor was my advisor, so I know him quite well. So yeah, and he was modeling the same task that we are recording now here in the monkeys. So yeah.
So, but your advisor at the WAM? No, in
No, postdoc after I finished my PhD, I was with him for a while in Madrid.
He's in Madrid. So
Yeah, Nestor.
WAM
But
is not the
Nestor,
WAM. I thought it was WAM from Mexico. No, it's WAM
no. Nestor is from Argentina,
University of Madrid. Okay.
yeah, but then he moved to Madrid, and he was the advisor of my advisor, my PhD advisor too. So
Okay.
so I know him quite well.
Got it.
Okay.
Can you send me the paper from by email so that I can
Yeah,
mention it?
yeah. Sí, te lo mando. I send it.
Okay, thank you. Okay, I'm going.
Bye, Alessio.
Thank you very much, Professor.
Professor. Yeah, I like that.
Thank you all, and